Next, it is equivalent joint loads. So the analysis by flexibility and stiffness methods requires the load must act only at the joints. Generally, we can uh, try for the displacements as well as rotations. Thus, the loads acting on the members, that is, loads that are not acting on the joints, must be replaced by the equivalent loads acting at the joint. The loads that are determined from loads on the members are called as the equivalent joint load. So, if you have a UDL, or if you have an incline load, or even at the load at the midspan, you are supposed to shift the load from the like the in between the supports to the support in an as an equivalent joint load. The equivalent joint loads are added to the actual joint load to get the combined joint load. That is, actual joint load, they are the loads which are directly acting on supports. So that will be always there. Plus the forces which are loads which are acting in between the supports are converted to an equivalent joint load. Combine the actual load plus equivalent joint load to get the combined joint load. And the analysis should be carried out for the combined joint load. The combined joint load can be evaluated such that the resulting displacements of the structure are same as the displacements produced by the actual loads. It's actually the theorem of superposition, where the total deflection is equal to sum of the individual displacements. This is achieved through the use of fixed actions to get the equivalent joint load. It's a procedure finding the equivalent joint load, which we will study in the upcoming slides. The fixed ended actions are the reactions at the end of the member considering its end to be fixed. It's actually a replica of the previous slide. So the fixed end actions. We have already learned the fixed end bending moment and the reactions for various load combinations. For the beam with UDL, W kilometer per meter with fixed end supports, the fixed end moments are WL square by 12 at both sides and WL by 2. This total W into L, total load by 2 to 2 supports will be the reaction in the case of UDL. And in the case of a middle point load like this, which has to be made to equivalent joint load for analyzing the flexibility and the stiffness metrics, for this type of load, the moment at both the supports will be PL by 8, TL by 8, and the reaction will be P by 2 for both supports. Similarly, if the load acting is an eccentric one, which is a distance of A from the support and B from the right support, the corresponding moment are PA square, PAB square by L square for the left support, and for the right support it is PA square B by L square. Similarly, the reactions are PB by L plus M1 minus M2 by L. The right support reaction is PA by L plus M2 minus M1 by L. These reactions, there is a support reaction as well as a moment, has to be learned by heart. We already studied the derivations in the previous classes, that is the previous semesters, for the eccentric couple and for the middle couple. So the middle couple is a special case where the A is equal to B is equal to L by 2. The general equation for the moment is MB by L square into 2A minus B. Similarly, for the right support, it is MA by L square into 2B minus A. The reactions are 6MAB by L cube. One is upward, one is downward. And if it's a middle couple, that A is equal to B is equal to L by 2, substituting M by 4 moments, and 3M by 2L will be the reactions. Yeah. So now we are focusing on the problem, the equivalent joint loads example 1. So we can see this from this figure that the load P2 is acting at the free end, it's okay, but P1 is not acting at a enough joint, so this has to be separated to an equivalent joint load. The M1 is okay, acting at a joint, but the UDL is also has to be converted to an equivalent joint load. So these are the beam with the actual applied loads. P1, P2 forces M and W real, L by 2, L by 2 distances. And the actual joint loads are acting at the joints are M1 and P2 only. So this should be added with the equivalent joint load produced by this UDL and the P1, which will be studying in the next slide. So these are the applied load other than the joint load, which has to be converted to the equivalent joint load. Yeah. So we are separating the beam to AB and BC. So AB is loaded with the UDL, BC is loaded with the point load at the middle. So for this case, WL square by 12, WL square by 12, which we have studied previously, right here is written, and WL by 2. All the moments, reaction moment and reaction supports are written, and for the single pointer also the same moments and the end reactions are reported. So these are the member fixed end action due to the applied load other than the joint load. So just combining both, because both are acting in the same beam, so we are combining this 1 plus 2 to get the total fixed end action for the entire beam. So in that case, the left side WL square by 2, WL square by 2 will be here, same, and WL by 2 here. W loading is also shown there. Then yeah, this is actually WL square by 12 is in clockwise direction, and PL by 8 is in anti-clockwise direction. So treating in anti-clockwise positive, P1 L by 8 minus WL square by 12, the reaction will be just added up between these two. For the right support also PL by 2, P1 by 2, and PL by P1 into L by 2 will be the moment. So this actually combined, yeah, this will be combined and written in the second figure. Then the equivalent joint load which we are finding out will be always negative to the fixed end reaction. So please note that this will be the fixed end reaction. All the reactions as well as the moment should be applied in a negative direction. So this reaction, as it is acting upwards, the equivalent joint load will be downwards. This moment being anti-clockwise, in the equivalent joint load it will be clockwise. So those things are affected in the next um, next figure. Equivalent joint load, negative of fixed ended joints, and then you have to combine the joint load, that is including the this was the actual joint load, right? So this should be added with our obtained new equivalent joint load to give the combined joint load. So yeah, so we have M1 P2 terms also coming in the combined joint load, which is applied joint load plus the equivalent joint load. So this is the procedure. So we know that the actual joint load are acting at the joints. The forces that are acting apart, like away from the joints, has to be converted to an equivalent joint load through this fixed and moment approach. Then add the actual load plus the equivalent joint load to get the combined joint load. Also note that the equivalent joint load will be always the negative of the fixed and reactions. There are the main takeaways or main key points in analyzing the equivalent joint load. So this will be some more big one, big problem. You can see the 40 is in AB beam, 120 is in BC and CD. So all the loads are actually not acting at the joint. So there is no actual load actual load is equal to 0. There are only the we can convert the individual loads to an equivalent joint load. So this one we have already discussed, the moment and the reaction. This will be an eccentric case because this is actually 4 meter, this is 6 meter, and this is also an discussed thing. So we know the end moments and the reaction. Yeah. Then you should club all these one to get the final fixed ended action. Yeah, final fixed end actions for the entire beam. The reactions are added together, which the mid one will be the sharing one, right? So it will be added both, and the end one will be in individual values like 240. So this 240 plus 88.89, 31 plus 120 separate. Then the moments are also added in a similar way, taking anti-clockwise positive and the clockwise negative. So this will be the resultant moments. Then next step, remind that the equivalent joint node will be the negative of this fixed end moment. So all the reactions should be reversed. So this is actually anti-upwards. In the equivalent joint node, it will be downward. This moment being anti-clockwise. In the equivalent joint node, it will be clockwise. Yeah. So those things are noted in the equivalent joint node, which is opposite of the fixed ended action. The combined joint loads are same as equivalent joint load here, since there are no loads applied on the joints directly. So this is actually the final analyze the equivalent joint load. Then you can write for the flexibility matrix or the stiffness matrix as the case may be. So the superposition of the combined joint load and the restrained actions gives the actual loading on the structure. Hence, superposition of the joint displacement due to the combined joint load and the restrained actions must give the actual displacements of the structure. But the joint displacement due to the restrained action are 0, because if there is a hinge there, definitely the deflection will be 0. Thus, joint displacements due to the combined joint load will give you the actual displacements of the structure. Combined joint load is the one to be analyzed, which will give the actual displacement. However, actual member and reactions are obtained by superimposing the restrained action and the member and actions due to the combined joint. We'll analyze a problem to make it more clear. It's a frame, so we are shifting from the beam to the frame. We have the load 50, which is acting at the joint, so there is no need to convert it. But for the BC beam, it is actually in between the support, so we need to convert it to the equivalent joint load. Then no other loads are there. Okay, so this 50. Okay, so the actual load will be the 50. Then the equivalent joint load we have obtained by differentiate from the this 30 and club it to get the combined joint load. So the fixed end reactions are this is actually WL square by 12 and WL by 2, which you have seen previously. Okay, this will be the ideal case like for this one here, like this case UDL, and this will be the fixed ended action. Then the combined action, that is you are actually including the 50 also here to get the combined one. These are the combined joint load, and you're supposed to find only that one for this problem. Another problem, problem number 3, here also UDL point load, one more UDL is there. So you need to convert this one to equivalent joint load, this one to equivalent joint load, this being a free end, so it can be taken directly. So we have two beams AB and BC of focus, which has to be converted to an equivalent joint load, where AB and BC are there. You know the individual fixed ended action. Then club both AB and BC to get the equivalent joint load. So to get the equivalent joint load, you should get the negative. Actually, one step is skipped here. As we are understood the procedure for finding the fixed interaction, you should add the both the beams, then you should apply the negative to get the equivalent joint load, and then the actual joint load, which is this 100 is added here to get the combined joint load. This is a summary. So we learned the basics of the metrics analysis of structures, static and kinematic indeterminacy definitions, the force and the displacement method. Otherwise, it is the flexibility and the stiffness methods of analysis. Definition of the flexibility and the stiffness. Definition of flexibility and stiffness influence coefficient. Concept of the physical approach to solve a single problem we have learned for a cantilever with a uh, like the tip load of p load and the momentum. So these are the basic things. Okay. Now in this module we will be learning some fundamentals of the flexibility method in detail, and the next module we are focusing on the number 3, we are focusing on the stiffness method entirely, and the fourth module will be a direct stiffness method approach. So the fundamentals of flexibility method introduction. This method is generalization of the Maxwell-Moore method in 1874. The unknowns are the redundant actions which are arbitrarily chosen, not conducive to computer programming because of the choice of redundant is not unique. Okay. We will see this problem. The flexibility method, basic concept, example 1, a single redundant continuous two span beam. So we could have analyzed this beam if this support is not there. This support makes the beam redundant to 1 degree, because here two unknowns are there, here one unknown is there, here also one unknown is there. So 4 unknowns, 3 equations will give you redundancy to degree 1, which is not here. So how to find the redundant? There's a reaction force here, so which is unknown to us. So first we need to remove the support B, that is shown in the release structure A, B, C. The support is removed here. This is the release structure. We know for the UDL the maximum deflection will be 5W L raised to 4 by 384 A. This should be remembered, and you have learned this one in the previous classes. So the deflection of the release structure due to the actual loads is given by delta B. Delta B. And also note that in the actual case the deflection at this point is 0 because there is a support there. So in the next stage you should apply an unit load corresponding to RB, which is redundant. So applying a unit force 1, then the displacement due to the unit load delta B is equal to, is actually PLQ by 48 TA for a simple supporter beam with a P load. For P is equal to 1, it is actually the P will tend to 1 and is LQ by 48 TA. The displacement due to RB is RB into delta B, force into the deflection. Hence, deflection of the release structure due to the redundant applied as a load. So we have the compatibility condition which should be analyzed in the flexibility method, that is delta B plus RB into delta B is equal to 0. This is the compatibility condition. So the net deflection at this point will be 0. We know the value of delta B. We know the value of a small delta B. And from that one we get RB is equal to 5W L by 8. So we found the reaction, and in this one the delta B is the flexibility coefficient, displacement due to the unit load corresponding to the RB. So this is actually an application of flexibility method in solving the structure. So there is a case of more than one redundant, that is this is a cantilever beam with actually 2 proppings are there, 1 and 2, which will make the this is actually three unknowns at this point, one unknown here, one unknown here. So this is 2 is the static indeterminacy of the structure, and here the q1 and q2 are the redundants. So the p1 is there, p2 is there. Okay. So first step, you should remove the redundants. That is, you should remove the support from the B and you should remove the support from the C. So once you remove the support from the B and support from the C, you will get a different shape like this, with delta B here, delta C here, and the P will be just transferred to the bottom. So these are the deflections corresponding to the redundants. Delta B and delta C are the displacements in the restructure corresponding to the redundants due to the external load. Then to solve for the we want to find the RB and RC, right? So for finding the RB and RC, we have to split into two. In the first case, you should apply an unit load in the position of the B, and second case you should apply the unit load in the position of the C. So we know that due to the presence of this reaction at B as well as C, the net deflection will be 0, which is the compatibility condition. That is, this is actually the actual displacement if there is no support, delta B and delta C. So this reaction actually is preventing the beam to bend in this way, right? So delta B plus F11 Q1 plus F12 Q2, which is actually the displacement here, and delta C is the free displacement, plus F21 Q1 plus F22 Q2 is the displacement at the point here, is equal to 0. Then we are making this one into a flexibility matrix form, delta B delta C plus F11 F12 F21 F22 into Q1 Q2 is equal to 0. This we can solve to find the reactions once the P1 and P2 are given to you. Okay, so the total deflection delta is delta P delta C is a matrix. Delta plus F into Q is equal to 0. That is, delta plus F into Q is equal to 0. F is equal to the flexibility matrix, and Q is actually the redundant matrix Q1 Q2. Q is equal to F inverse of delta. If there are support displacement, so now we were thinking of the case there is no deflection for the support. If suppose in the question it is telling that there is a support is actually settling by 2 mm, then this compatibility condition should ensure that there is a resultant displacement which is not at all 0. This 0 has to be replaced by the displacement given, support displacement given at the point. So it is actually an extended equation including the support displacement. Q is equal to F inverse of S minus delta. Okay.